So we've been working on gas laws, and now we're going to make them extra useful by combining them all together. The three laws we've looked at, Avogadro's law, Charles' law, and Boyle's law, we're going to take all of these equations and put them together into what we call the combined gas law. And this is going to allow us to change a few different variables at a time. We can change pressure, volume, temperature, and moles all at once, and we're not limited to trying to keep certain variables constant. As you discover these problems, you want to look out for the fact that there's going to be two different sets of conditions. There's going to be the before and the after, and we want to make sure that the units on both sides match so that they can cancel each other out. Same basic approach to solving these problems. Look at your variables, write and rearrange your equation, and then it's harder to solve these conceptually, so you want to be really careful with your math and your calculations as you do these. So let's take a look at the problem here. A scuba diver 40 feet under the water inhales 50 mils of compressed air, so that's volume 1, in a scuba tank at a pressure of 3 atmospheres, so this is going with this first set of conditions, and a temperature of 8 degrees. And before we forget, we know we always have to go to Kelvin, so let's just convert that to Kelvin, which is 281.2 Kelvin. What is the pressure? So P2, I don't know, of the air in the lungs if the gas expands to 150 mils at a body temperature, this is T2, of 37.0 degrees. And again, we'll add 273.15, and that gives us 310.2 Kelvin. So I've got all kinds of variables. One variable that I notice is not being used here is there's no mention of moles, so it's the same gas bubble that's small and then it is expanding. So I can just ignore the ends. And then I want to think about which variable I'm changing here. And that's going to be my P2, or sorry, what I'm solving for. That's going to be my P2 is what I'm looking for. So I'm going to go off to the side and just solve for P2 real quick. So P1 V1 over T1 equals P2 V2 times T2. I want to multiply that T2 up, so P1 V1 over T1 and then times T2 equals P2 V2, and then to get P2 by itself, divide both sides by V2. So P2 is equal to P1 V1 T2 T1 V2. So that's going to be my equation that I want to plug numbers into. Again, just careful attention to detail like you would do in a math class is going to keep you out of trouble. In terms of other units, so I've got the Kelvin units. I noticed that my volume units match. They're both in mils, and milliliters is fine. I don't need to convert it to liters because I'm not using the gas constant, which we'll see in a later problem. So now that I've got all this, I'm going to plug it into this equation here. So P1 V1 T2 T1 V2 is going to give me that pressure that I need. 3.00 atmospheres, and I'm just going to spill over into this space here, times 50.0 mils times my T2, which is 310.2 Kelvin, divided by T1, 281.2 Kelvin, and also divided by V2, which is 150 mils. Look for your units to cancel, so kelvins will cancel, mils will cancel, and I'm left with atmospheres. And so this ends up giving me a total pressure, P2, of 1.10 atmospheres. We know that this is around atmospheric pressure, so anything that's in your body should be ballpark near atmospheric pressure. You shouldn't have 100 atmospheres. That would explode the tissue in your lungs, or something really low. You wouldn't be able to breathe if you had too low of a pressure. So the fact that this is somewhere near atmospheric pressure in your body is a good conceptual thing. The next problem below this is one you can practice. So same idea. Here you're looking for a final temperature, and they give you changes in volumes and changes in pressure and an initial temperature. Watch out, your temperature has to be in Kelvin as you solve the problem. And this doesn't specify, but I would say work on solving for a final temperature in Celsius as you do this for practice. So that is taking all those gas laws, combining them into one. We could use it with moles also, and then you're able to solve a huge amount of different types of problems.